already know a lot of this stuff. I'm just going to give you a few new pieces of information. We're going to talk about a couple new calculations, but the calculations are basically algebra based, just pH calculations, kind of plug and chug. The hardest part about pH calculations is figuring out how to type it in the calculator, and that's it. I'm not expecting you to know how to graph logs or how to do like legit math with logarithms. I'm just asking you to find the button on the calculator and press it. Okay, there's one more sig fig rule. You thought you learned all the sig fig rules, didn't you? But guess what? You have another one. Isn't that what a lovely treat that you have another sig fig rule? Isn't that lovely? All right, so really quickly, we're just going to go through some things you can read through. You can read all of this. I'm not going to just read it to you. Properties of acids. You know an acid, lemon juice. Okay, you've done an acid and metal, zinc, and I think you used vinegar. Vinegar, yeah. So zinc and acid, you saw it bubble in your reactions lab. You watched a video of that, so you all know this stuff. Litmus paper is just a test of acid or base character. Don't worry about, we really don't use litmus paper anymore, but it's still in the textbook, so it's here in the slides because these slides are from the textbook. But have you ever heard somebody say, oh, that's a litmus test for this? It's like a yes or no test. Litmus paper, if it turns red, it's an acid. If it turns blue, it's a base. Like, it's a yes or no test. Bases are like soap. So I want you to think about soap for a base. If you've ever gotten soap in your mouth, you know bases taste bitter, they're slippery, and they make litmus paper blue. Caffeine is an example of a base, but there are a lot of other bases. You need to memorize 6 strong bases and then 2 weak bases. So hopefully that's on your list of things to do before Thursday. A couple different definitions of acid. The first is Arrhenius. That's how you say that, Arrhenius. And Arrhenius said, hey, I think an acid is anything that makes H+. So if it makes hydrogen ions, it's an acid. And so because hydrochloric acid or hydrogen chloride breaks down into hydrogen and chloride, it makes H+. So because it makes H+, it's considered an acid. So Arrhenius really kind of talks about what is the substance made of. Does it have H+? Because in order to make H+, you probably have to have it. And then you need to know one thing here for your memory quiz. Hydrogen is equal to hydronium. Hydronium is this thing here when it's in water. So in water, hydrogen cannot exist. So I hate this. I hate this stupid dot configuration. I'm always yelling at y'all to not do these dang dots. Don't do these dots. They're confusing for me because I cannot see what you're talking about with your dots, and you don't know what you're talking about with the dots. Nobody knows what's going on with these dots. Draw water with lines connected to the H, not dots between for bonds. Let me just kind of redo this here. And then hydronium, you did this for your lab, is going to be this trigonal pyramid. Okay, get rid of that, those dots. I hate that. Okay, for this, why does this happen? So let's say we have water and we stick some H+ in that water. Why does the water want to grab that H? That H+. Help me out. Faster y'all throw out guesses, the faster this class goes. Wyatt, what you think?
Why the water wants to grab the H+?
Uh-huh.
I thought it was something, then I think it's wrong, so I was thinking something else.
Oh no. Well, if you think maybe that this oxygen right here is real negative. So y'all are getting there.
Oh, the negative of the oxygen.
Oh yeah, look at that full positive charge right there. It's beautiful. The negative oxygen is super attracted to that full positive charge. That's an ion dipole interaction, y'all. And it is such a strong interaction that those electrons are just gonna make a bond between that H. So you're gonna take these electrons right here and they turn into this bond right here. See that? So they're just going to bond right to it. The hydrogen ion does not have any electrons. It's just a proton. So that's why they're so attracted to that, because the purest form of positivity is the hydrogen ion. And so the water sees that and it snatches it up. So you cannot have hydrogen ions existing in water as H+. They always exist in water as hydronium H3O+, because the water will snatch it right up. So that's why we say they're kind of equal to each other when they're in water. So 1 hydronium equals 1 hydrogen ion, vice versa. They have a 1-to-1 ratio. So we can just kind of think about them as being equal. So Arrhenius means it gives off H+ or makes hydronium, essentially. Arrhenius talked about bases too, and he said that bases are going to be things that give off hydroxide. So I want you to think about an acid part of an Arrhenius definition is the hydrogen ion, and the base part of this definition is hydroxide. They're kind of opposites. Do you see why water is considered neutral? So you may see that? What happens when I get H+ and OH- together? What do they make? Y'all know this. You talked about your net ionics. We did all this already. See, cumulative. H+ plus OH makes HO2, H2O, OH2, H2O. Yes. So that's why water is neutral, because it has an acid part and it has a base part, so they cancel out. So pretty much Arrhenius said, hey, anybody with an OH is a base. Okay. Because of this reason. So here's your acid part. Here's your base part. Here's my neutral. H, OH makes water. Okay. But that definition is not inclusive, and we want to be inclusive because there are some bases that don't have hydroxide, like two that you're memorizing. You're memorizing ammonia and you're memorizing the bicarbonate ion as 2 weak bases. And they're basic, but they don't have hydroxide. So the Arrhenius definition isn't very inclusive of them. So a better definition for acids and bases, and one that we're going to use a lot in this class, is another definition called a Lewis definition, and you'll learn that a little bit later. But the better definition for us in this class is going to be Bronstead Lowry definition. This definition talks not about what an acid or a base looks like, what is contained in that acid or base, but how an acid and base behaves. It defines the job of the acid and the base. So the job of an acid, the job description, is to donate a proton. Okay, look at this reaction here. I see a proton in this reaction. Do you see a proton in this reaction being exchanged? So hold on, we're talking about like hydrogen and hydronium, and we're talking about hydroxide, and now we're talking about protons? Yes, Heather. H+ is a proton, y'all. Think about it. An H atom has how many protons? 1 proton. How many neutrons? Yes, Jeremiah, y'all know I cannot trick you. 0 neutrons. How many electrons in a hydrogen atom? Look at this final exam review we're doing. A hydrogen atom. Nina, not when it's stable, but when it's just chilling by itself. 1 electron. So, what about a hydrogen ion? What do I do to make it a hydrogen ion? What do you do to make a hydrogen atom into a hydrogen ion? Gotta lose that electron. Yep, we're a cation. So we're just gonna be 1 proton, no electron. A hydrogen ion is a proton. So we say proton, we mean hydrogen ion, same thing. The job of an acid is to donate that H+, okay? The job of a base is to accept it. So now we're defined not by how we look, but by how we behave, which is more inclusive. We can include ammonia now and bicarbonate now into these definitions. You can also tell a little bit about what's going on by looking at a reaction. So take a look at this first reaction here. Do you see where the hydrogen is being donated and where the hydrogen is being accepted? So let's track this hydrogen right here. The hydrogen is with the chlorine. And if you look on the right side, where'd the hydrogen go? It went with the water. Do you see how H2O became H3O? So that means water gains an electron. Gained a hydrogen. That means water is acting as an acid or a base if water is gaining an H, gaining a hydrogen. Is that the job of an acid or a base to gain a base? So water is acting as a base here. Here's the thing about water. Water wants to hang out with you and it will do whatever it can. Water goes, oh, you want me to be your base? I'll be your base. Water says, you want me to be your acid? I'll be your acid. So water, because it's neutral, can behave in both ways. We call that property amphoteric, meaning it can be either one. And amphoteric is later in your slides. So here's that hydrogen right here. It's hanging out as part of hydronium. With the other reaction down here, which hydrogen is being donated? One in the ammonia or one in the water? The hydrogen that's being donated is one of the ones in the ammonia or one of the ones in the water? If the hydrogen is being donated, there's two, in the forward direction of this reaction. So this reaction, if you see these double-sided arrows, means the reaction goes back and forth. So the reaction in the forward direction, so reading it just left to right, this is your H being donated. Okay, it's being given to the ammonia because you see this is NH3 turning into NH4. In the reverse direction, the ammonium is giving up the H. So we'll talk about reverse direction in just a second. Oh, you're still looking at the top. So another definition that we need for this is called conjugate. A conjugate, y'all, don't be afraid of this big word, means a partner. So the partner of a base is the version of it that's the acid version of it. So you have kind of two parts to yourself. You have a base version and an acid version. If you let the base do its job and add H, it becomes an acid because now it has an H to give. Does that make sense? So like, okay, if I'm a base, I do not have an H to give. So I accept an H. This is my H. Now I have an H to give. Can I donate my H? Sure can. Now I act as an acid. So if I'm a base and I do my job of accepting the H, now I have an H to give and I can donate it. So in a reaction that's reversible, what once was your base can now behave as your acid because once you have those hydrogens transferred, now, because I acted as a base at the beginning, now I have an acid to donate. So the conjugate is just a partner of that. So to tell conjugates, you have a couple ways you can do that. So the one way to tell conjugates is to look at your reaction in reverse. So if we look at this reaction this way, which H is being given? One from the ammonium or one from the hydroxide? If we look at this reaction in reverse, the way I have the ammonium, here's the H is being given. Do you see that? So we call it the acid because it's the one that's giving the H. The other one must be the base because it's accepting the H. The hydroxide is gaining a hydrogen to become water. The ammonium is losing a hydrogen to become ammonia. So, but we can't call ammonium the acid because it's a product. It's on the right side. So if it's on the right side, we call it a conjugate acid. That's one trick. So if you have a reaction, just look at your reaction in reverse. and do the same thing you would do in the forward direction to identify your acid and your base. And again, we're identifying acids and bases based on their jobs. So look at who is donating H and who is accepting H. That's your big thing. So focus in on that. If you can remember that, you can get all of this other stuff. It seems a little complicated, but just go in on the basics. An acid's job is to donate H. A base's job is to accept H. Whoever is donating H must be an acid. Whoever is accepting H must be a base. And looking at the reaction forward to identify acid and base, and looking at the reaction in reverse to identify conjugate acids and bases. It is simple, but it is easy to make complicated. I made it very complicated and did not really understand it simply until I was in grad school, and I was very embarrassed when I got into grad school and could not really identify conjugates very well. Okay, so don't be like me. Understand it as simple and leave it as simple in your head. Do not try to overcomplicate it. Don't try to make it harder than it is, because conjugate, the word itself is kind of weird. It's just the acid or the base in reverse, or the result of the acid or base doing its job. So the second way you can tell a conjugate, so I will give you questions like this on an exam, multiple choice or something. I'll give you a reaction. You tell me what's the acid, what's the base, what's the conjugate acid, what's the conjugate base. It's going to be in your problem set as well. The other way to tell is by just letting the stuff do its job. So to find a conjugate acid from a base, let the base do its job. So other way to assign conjugates. So let the acid or base do their job. And whatever is left over is the conjugate. So think about taking a base, okay? So take a base. What's the job of a base? A base job is to do what?
Accept H.
Accept an H. So let it do that. Add an H to your base. What do you get when you add an H to NH3? NH4. Don't forget to also add a plus. So I like to think about it like this in two parts, okay? I'm going to take my NH3, I'm going to add an H. That makes NH4. Don't make it more complicated than that. Second part, though, I have to remember is I'm not just adding H, I'm adding H plus. What is the current charge on ammonia? What is the current charge on ammonia? Yes, Heather, man, my last class last night, they were all over the place. +1, -1. They're trying to just do anything to get the right answer. And I was like, y'all, it's neutral. And they're like, what? It is neutral. If you do not have a charge, you're neutral. Ammonia does not have a charge. It is not a polyatomic ion. So I have a neutral thing. I'm adding +1. What's the charge of ammonium? +1. Think about the math. 0 plus +1 equals +1. Make sense? Hopefully. Add an H, add a plus to a base. Let the base accept the H, let the base accept the plus, okay? Whatever it makes when it does that is your conjugate acid. Same thing we can do for our conjugate acid. Let the acid do its job. Acid has one job. Donate H plus. So we're going to remove H plus. So you have H2O minus H. Gives you OH. Then we got to think about our charge. What's the charge on water? Just copy paste. 0. Charge on H plus, so plus 0 minus +1 is -1. Get a number line out if you need to. It's fine. Do what you got to do. Let it stay as simple as this in your head so that when you get to upper level chemistry in graduate school, you're not embarrassed like I was with identifying conjugates. All right. Let the acid base just do their thing. And whatever they make when they do that, that's the conjugate that goes with it. That's
So
it.
donating a proton is like subtracting though?
Donating a proton is subtracting a proton, yes.
Okay.
Okay, subtracting that H. Right, so if I donate money, it gets subtracted from my bank account.
Okay, and then you become negative, yeah. Okay.
And if I donate too much money, then I become negative in my bank account, right? Okay. So here's another example. I like this example because a lot of people, if you say, hey, what's the conjugate base of sulfuric acid? A lot of people say, if this is the acid, the conjugate base is sulfate. Because some people just do this trick where they say, well, you just take away the H's. That's your conjugate base. Okay. That's not true. That's not the conjugate base here. The only difference between correct conjugate acid base pairs, one H and one charge. Only one. The difference here, it has a -2 charge difference, and it has a -2 H difference. And that's too large of a difference to be considered correct conjugate pairs. Okay, acids are really nice, and they donate all the time. But you'll find in just a second that not all acids are as nice as they seem to be. Questions about conjugates? It's kind of hard because the name is hard, but really just focus in on that definition of acids and bases, let it do its thing, and the conjugates are made a lot easier. And again, if you have questions that you're kind of thinking about or writing out, you can text me or email me as well. Y'all know about neutralization examples here. You have plenty in your problem set. I'm gonna let you just kind of dive in that way. Yeah. We have a lot to cover today, so I'll let you get into your problem set examples there. Just keep these kind of around as notes. Y'all know about neutralization reactions. They are double replacements. You cannot see that. They are double replacement reactions. Just a double replacement between an acid and a base makes a salt. A salt is an ionic compound that is made from an acid and a base. If you say, pass a salt to a chemist, they're going to ask you which one. Because table salt is specifically only sodium chloride. So salt is a term that encompasses thousands and thousands of chemical compounds. So don't be in the lab and say, hey, pass the salt, because it could be anything. If you're talking about sodium chloride, you can say common salt, table salt, or sodium chloride. Acid plus a base makes water and a salt, which is just an ionic compound that comes from a neutralization reaction. That's all that is. You already know about this because we did all that reaction stuff. Look at that cumulative. Y'all already know how to do this. You know how to do a titration. A titration is a process from which we are finding an unknown concentration of something. What are we going to use for concentration probably? What unit? What unit did we just learn about concentration? Probably molarity, right? That's concentration. Remember, molarity is mole solute over liter solution. Just a quick reminder, you can do concentration in mass percent as well, but typically concentration is going to be in molarity when we're just kind of doing things in the lab, right? So find an unknown molarity with a known molarity. Y'all already know how to do this. We did this at the end of chapter 13. So again, like there's a lot of overlap here. I'm going to let you kind of go through the lab for this week, which is your titration lab. It's going to get more in detail into this. They're going to show you the video. I've also provided you with several simulations and animations on the chapter 14 module on Canvas that I encourage you to kind of check out. This is one of those kind of skills that you really should have moving into Chem 11. So I highly encourage you to check out the simulation where you can kind of do it yourself and get an idea of you know, what it's like to do a titration, because it can be very frustrating and it's a good learning experience. So again, here's some more pictures of titrations. You're going to go through the whole lab, so I'm not going to stick too much into this. I'm not going to go through this, but I want you to look through this question on your own time. And I will, at the end of class today, come back and give you the work and answer for this. But if you cannot do M1V1 for this, you better not. I will make my own piece of paper that I'm going to pretend is your work, and I'm going to tear it in half if you do M1V1. Can I do M1V1? Why can I not do M1V1 here? Professor, I see M's and I see volumes. Why can't I do M1V1? Tell me why. It's not the same substance. You need a mole ratio. M1V1 does not do that. Now, if you do M1V1 for this particular reaction, you'll get the right answer. But I will take points off still because I'm just mean about it. This is my big thing. I'm not like super mean about a lot of things, but M1V1, man, that gets me pumped up and ready to fight. Don't use M1V1. I'll go back and give you the answer for this. Y'all can work this on your own. We got more other new math to cover. This is not new math. This is chapter 13 math. This is chapter 13 math. So I will go back and make sure that your notes have this so you can refer back to it, but I'm not going to spend time on it right now because you already know how to do this. This is nothing new. Okay. Back to the new stuff. We'll take a break in just a few minutes. Okay, we got these things called strong acids and strong bases, okay? A strong acid is really good at its job. Remind me what the job of an acid is? Yep, donating. So that means that when that acid hits that water, it is gonna 100% donate its hydrogens to the water, making hydronium and then whatever's left over. Okay, so we use one single arrow to designate this, meaning this reaction goes one way. It does not go back and forth. If I'm a strong acid, I donate and I don't ever take the donation back. So that implies that there are some acids that take the donation back. We'll talk about those, okay? So strong acids, they donate stuff and you will never find them at the Goodwill digging through their boxes trying to find the stuff they donated to take back, okay? They're gonna donate their stuff and they're gonna leave it alone. Donate it out of their mind. They're so good at this that they do it 100%. Everything they have, they donate. Okay, that's your true strong acid. Okay, strength has to do not with how dangerous an acid is. It has to do with how well does an acid do its job. Strong acids do their job 100%. Not strong acids are always dangerous. That's not true. You have stomach acid, and though your stomach does have a really, really good lining to keep that acid in there, and stomach acid will burn you if it gets up into your esophagus, that's what heartburn is, but it is not burning through your whole body, okay? You can have a weak acid that will dissolve your bones. You can have a strong acid that will not dissolve your bones. So strength has nothing to do with how dangerous or how easy it is to like dissolve metal or something with an acid. It has to do with, does it do its job? Okay. Just kind of putting that out there. I'm going to talk about it again when we talk about pH. If I make a whole bunch of ions, guess what I have? An electrolyte. We already know this. This is old news. Y'all know about electrolytes. Here's your list of strong acids. You're memorizing these for Thursday's memory quiz. Just a hint, these three are on the periodic table. So you can kind of use the periodic table to help you out with those, and then you can come up with something else if you want to figure out the other three. If it's not strong, it's weak. So you don't have to memorize any weak acids. Just know if it's not strong, it's weak. So what does a weak acid do then? Well, strong acids, they do their job 100%. They get A pluses, not even 99%. I mean 100% they do their job. They're your employee of the month. Weak acids, though, on the other hand, They're going to call themselves acids, but they're not very good at it. So they do their job. And you're going to think this is kind of, you think weak acids, okay, strong acids do their job 100%. What percentage do you think weak acids do their job? Strong acids, 100%. I donate 100%. Yo, it's like 1 to 5%. Y'all ever work with those people who do their job like 1 to 5%? They're weak, okay? They're not doing their job 100%. So I'm a weak acid when it comes to donating. I will go through my closet and Marie Kondo my whole apartment and be real excited about throwing away stuff and like, you know, thanking my things for giving me joy, and then like, you know, putting them in the box. And then I get to thinking about all the memories associated with that, or how one day I'm gonna fit in those pants. And I'm going back in the box and I'm pulling stuff out. I'm a weak acid. I do not donate 100%. Okay, I'll put substances, I'll donate, but then I'm digging back to the box. Okay, so weak acids, they donate and then they take it back. We designate this with a double-sided arrow. So we donate to the right and then we take it back to the left. This is where we get our conjugates. So with strong acids, you don't really actually have conjugates that do anything. So let's think about this. If I want to identify my conjugates here, hydronium or chloride? Go ahead and identify these with conjugates. So like, this is your acid, this is your base. Identify your conjugate acid and your conjugate base really quickly. Okay, hydronium. Is hydronium a conjugate acid or a conjugate base? Yeah, it would be the acid, right? You see that hydronium has an H. Chloride cannot be a conjugate because it cannot be a conjugate acid because it doesn't have H to give. Acids have to give H. The only one that has H over here is the hydronium. So it would be the conjugate acid. And that means chloride would be the conjugate base. Does this hydronium ever get to act as an acid? Does it get to act as an acid and give away its H and go in the reverse direction? Does hydronium ever get to give its H to chloride? No. This hydronium never gets to give its H to this chloride. So it never acts as a conjugate acid and it never acts as a conjugate base. So the conjugates of strong acids and bases never get to even act like that. So we don't really even consider them. Like chloride doesn't have any basic properties at all. Hydronium does have acid properties, but we're not gonna talk about that. Chloride, right, in this situation, these two things, they don't get to act like acids and bases. Because strong acids and strong bases go 100% to the right. They don't go back and forth. So only if you go back and forth is the thing that you're talking about, the conjugates get to do that job. So in this example though, this is my acid, this is my base, this is my conjugate acid, this is my conjugate base. The conjugate acid and base, they do their job more than the originals. It goes 1 to 5% this direction. Which means it must go 95 to 99% this direction. So actually, of the two acids, hydrofluoric and hydronium is a better acid than hydrofluoric. The weak acid makes the stronger conjugate base. Okay, so fluoride is a better base than HF is an acid. Okay, so fluoride is better at accepting hydrogen than hydrofluoric is at losing. This is really important when you move to organic chemistry because you talk about stability of acids based on their conjugate bases. So hydrofluoric acid has a really good conjugate base. So this is why it's not a strong acid, because the conjugate base is really good at being a base. So it wants to accept. It doesn't want to give. That's a little bit more advanced as far as like content goes. You just need to recognize weak stuff. You're going to use a two-sided arrow. And that means that it has partial ionization. So what I mean by partial is 1 to 5% dissociating. So does it make some ions? Yes. There are some ions in there. It makes some ions. But also stays as molecules. 99% usually stays at molecules, and like 1% turns into ions in weak stuff. So I have a little bit of charge. So you're going to call me a weak electrolyte, okay? Weak acids, weak electrolytes. Okay, so we got strong electrolytes. They're going to be ionic compounds and strong acids. Let me go write that up here. Strong electrolytes, ionic compounds, and strong acids. Okay, because they dissociate 100%. When they dissolve 100%. Weak acids are weak electrolytes. When they dissolve 1%, 2%, maybe 5% if you're lucky. Here are some weak acids. Don't gotta memorize them. Guess why? You know the strong, you know the weak. If it's not strong, it's weak. Okay, we're gonna take a quick break. I'm gonna come back and I'm gonna show you some pH math. You can talk, you can look at this if you want to. We're gonna kind of skip this because again, we already did this. Concentration, I'm gonna show you one cool thing about concentration as a shortcut, and then we'll get on with our pH math. So we're gonna take a quick break. All right. I realized I was recording. Sorry for those of y'all watching the recording. Just hopefully you either took a break or you fast forwarded 10 minutes. So determining the hydronium concentration in each solution, I'm going to give you a couple of notations. So notation here, brackets around something means concentration of that thing. And it just is awesome because it helps you so much in not writing the word concentration all the time. So if I want concentration of something, I will just write brackets around that thing. So brackets around A would be concentration of A, typically in molarity, typically. Okay. So determine the H3O plus concentration. I can get rid of this whole word and I can just write determine the H3O plus in brackets. And that would be the same thing as determining the concentration. So if it's a strong acid, you can use a simple mole ratio to determine concentration of hydronium. HA, or let's say HXA plus water gives you X hydroniums plus A minus. Okay, so what I'm looking for here is however many H's there are, that's how many hydroniums you get. So, for example, if I have one H, that's a 1-to-1 ratio. So because it's a 1-to-1 ratio, it's 1.5 molar hydronium, right? That's if it's strong, you can do that. So for another example here, I don't know why this is not an example. If I have 1.5 molar sulfuric acid, what is the concentration of hydronium? Yes, if you have 1.5 molar sulfuric acid, which is strong, what is the concentration of hydronium? You're following this formula. Whatever the number of H is the number of hydronium. So think about that ratio. So for every one mole of sulfuric, you have 2 moles of hydronium because there are 2 H's. So because there's a 2 here, there's a 2 here. So if you think about this, 1.5 mole of sulfuric per liter of solution, for every 1 mole of sulfuric, there's 2 mole of hydronium. So what is my concentration of hydronium? 3. Does that make sense? Take your concentration and just multiply it by the number of H's. So if it's strong, concentration, I can just write out brackets to my own shortcut, concentration of hydronium or concentration of hydrogen, right, is equal to concentration of the acid. Acid is usually written as HA times the number of H's. Probably can write that a little bit clearer. Okay, remember these are the same thing, is equal to the concentration of the acid times the number of H's. So you could just say 1.5 times 2 because there are 2 H's. I can say 1.5 times 1 because there's 1 H. if it's strong. If it's weak, you do that math, and then you just say less than. If weak, because it's back and forth, this is like 1%, and this is like 99%. So you can't actually do the math yet. There is math to be done to actually figure it out. So you're just going to guess. So we're just going to do an estimate. Just estimate less than, but don't actually give a number. So what I mean by that is literally just say less than. So for weak, this is acetic acid, it's weak. So you would say, if it were strong, H3O plus would be 3. Because it's weak, we're going to say H3O plus is less than 3. That's all you can say at this point. You can't give me more information than that because we're not going to do the whole thing. It involves the quadratic equation sometimes and other stuff. So less than 3. So all you can say is that it's less than. So because this is weak, we cannot say it can't be 3 because that would be if it were strong. Okay. Let me just kind of trying to designate here with color, but the strong number of H's times the concentration of the acid. If it's weak, same thing, do the math for strong. Say if it's strong and then do less than, estimate less than. So do the math for if it's strong and then just write less than instead of equals. Because again, I will not, and this is really important for doing any sort of calculations on an exam or anything. If you actually are giving me a number that's correct, I need to see how you're getting that number. Meaning I need to see the quadratic equation and how you're getting that number. Because otherwise it seems like you're just kind of looking it up. So otherwise I'm expecting everybody in this class to just say less than the number that it would be if it were strong. Okay. These are just mole ratios, or less than the mole ratio would give you. That's all. This is nothing new. It's just a mole ratio. Don't let it be more than that. It's just a mole ratio. Okay, strong bases are exactly the same as as strong acids. They dissociate 100%. They do their job 100%. You're going to have a list of strong bases to memorize. Here they are. Look at these. They're all the hydroxides that are aqueous. So you don't have to memorize these. They're on your periodic table. Because if you look at that solubility chart, any hydroxide that's AQ or soluble, that's a strong base. You'll memorize those. Weak bases do the same thing. Here's the generic equation for bases. They do the same thing as weak acids. They do their job 1 to 5% of the time. Same idea about their electrolytic abilities and all that kind of stuff. You need to know 2 weak bases, ammonia and bicarbonate. Those are the 2 you need to memorize. Everything else, don't worry about it till later. So these are all organic compounds. Okay. Same idea here. It's a mole ratio. I should say OH. strong or weak. I'm gonna let you go through this. I will make notes on this slide before I give them to you, but I'm gonna let you kind of go through this on your own time and kind of look at it is exactly the same as the hydronium concentration. You just kind of use a mole ratio. If it's weak, you just say less than, okay? So water acts as an acid or a base. We talked about that already, that it has a property that's called amphoteric. Okay. And because water has an acid and base properties, it has two pieces. So water has the acid piece and the base piece make water. It's consistent of two pieces, right? Remember, so this is your acid piece, it's your base piece. So water has two pieces, acid and base. That's what makes it neutral and also amphoteric, is it's able to give H because it has H, it's able to give OH because it has OH, it's able to accept H to become hydronium, kind of do everything. So we get some math here that you don't really have to know too much about how it's derived. You need to use it. So on your periodic tables, if you have those out, on the back of that periodic table, you have something that says KW equals, oh, you have this. Here, I'll just highlight what you have. You have this. This is called the equilibrium constant for water. And we're talking about equilibrium on Thursday. And it simply means that water is going back and forth between its acid part and its base part. So it's kind of going back and forth between hydronium and hydroxide. When its acid part equals its base part, it's neutral, okay? When acid part, which is your hydronium, equals your base part, which is your hydroxide. So when your hydroxide and hydronium are the same, that's neutral. And when they are the same, they are both this concentration. Okay, this is for water, for pure water at a certain temperature. And then we get this KW here. I will show you how to get that on Thursday, but by multiplying those two numbers together, we get this number. This is given to you. You need to add in your memory. This is equal to hydronium times hydroxide. Okay, not given to you, but you should know. We'll talk about how I get that formula for this K value. But for right now, just know that when I take the acid part and multiply it by the base part, when they are neutral, when they are the same, they equal 10 to the negative 14. And that helps me because when they're not neutral, when the acid part's bigger than the base part, they're still going to equal 10 to the negative 14. So it helps me figure out how much acid part and how much base part I have in a non-neutral situation. So for right here, for right now, if you're like kind of overwhelmed, this is what you have. Make sure you know this number is equal to hydronium times hydroxide. Okay, acid part times base part. And remember that these brackets mean concentration. So I'm going to do one of these and then let you do the rest of them, and I'll finish the rest of these on the presentation before I tell you. But I want to know the hydroxide concentration. So what I'm going to remember is 1 times 10 to the negative 14 is equal to hydronium times hydroxide. Okay, I know this looks complicated. It's the same thing as saying 4 is equal to x times y. Can you solve for y? Rearrange 4 equals x times y to solve for y. What is it? Give me another 15 minutes. 4 over x. Okay, you could do that. You could solve for hydroxide. It's the same thing. Okay, so hydroxide is going to equal 1 times 10 to the negative 14 over hydronium. That's it. Same thing. Same math. Just now we're dealing with really small numbers in scientific notation. So I'm going to look at A. My hydroxide is equal to 1 times 10 to the negative 14 over my hydronium. My hydronium is 7.5 times 10 to the negative 5. You run into problems here when you do not put these in your calculator correctly. But the math itself is 4 equals x times y. That's it. So go ahead and plug this into your calculator. And I want to make sure that you are getting the right answer. That means you're using your calculator correctly. And check your sig figs. You're always going to use your sig figs from this number. The 1.0 is infinite sig figs. So don't use sig figs for that. And it's concentration, so it has a unit. You're not getting this. You're putting this in your calculator wrong. Make sure that you're using EE or EXP. And make sure you are not using times 10 to the, unless you are using parentheses. Okay? If you're not getting it, text me or something. We can go through your calculator, make sure we're troubleshooting. Okay? Sig figs are going to be the same as your hydronium concentration. This 1 times 10 to the, here, let me just move this around. This is infinite sig figs. So don't count it. It's just a constant, okay? I'm gonna let you do the rest of these. I'll make sure that they're on the slides, but you can do the rest of them on your own. So this brings us to pH, and most people have heard of pH, but maybe we don't understand exactly what it is. If something is more acidic, it has a certain pH, or more basic, it has a certain pH. So look at these numbers. Which of these, let's say 10 to the negative, let's just do a quick little, make sure we got this, 10 to the negative 5 versus 10 to the negative 8. Which one is bigger? Which is a bigger value? If you get confused with this, remember, negative values are like your bank account. It is better to have less negative in the bank. So if I have negative 5 versus negative 8, I'd rather have negative 5, so that's more money. Okay, it's less the opposite of money, right? So negative 5 is bigger than negative 10. So if you go down here, negative 0 is bigger than negative 1, right? So all of these are kind of getting bigger as you go down. That means that as your hydronium increases, your acidity increases, and that should make sense to you because this is your acid part. So as my acid part is higher, highest concentration of acid part, I'm more acidic. My lower concentration of acid part is more basic. Remember, this is my base part. My high concentration of base part is basic. My low concentration of base part is acidic. So kind of ground ourselves really quick. If it's got a lot of base stuff, it's basic. If it doesn't have a lot of base stuff, it's more acidic. And then we have a little area in the middle that we call neutral. Remember that 10 to the negative 7 before? That we just had on that last slide, 2 slides ago right here, 10 to the negative 7, that's neutral. There it is, neutral. Technically neutral is more of a kind of area around there, but for us for this class right now, that's neutral. pH is a scale of hydrogen or hydronium. pH is equal to the negative log of H. And you know that H is also hydronium. So it's the concentration, the negative log of the concentration of hydronium. So that means as you have more hydronium, your pH goes down. So more acid stuff means a lower pH. Okay, so strongly acidic is at the bottom, strongly basic is at the top. pH scale goes from 0 to 14. And you may know a little bit of this already. Do not be afraid of this equation. Just press the button on your calculator. Just log and then the number of your concentration. The same kind of concentrations we've been kind of playing around with here. Okay. P means negative log. Now I want you to remember this because we're going to be using P of other things. P is equal to negative log. So the pH, that's the negative log of H. What's the POH? The negative log of what? OH. P of something is a negative log of that thing. That's what it means. Somebody was doing their math, they just denoted P, so that's what we took it for. So pH is a base 10 scale. This is kind of like the earthquake Richter scale. A pH of 2 is 10 times more acidic than a pH of 3. pH of 2 is 10 times more acidic than pH of 3. So if you're moving pH scale, that's not just one little piece. That's a lot. It's a lot of hydroniums that you're adding in there. Okay. So we're going to do a really quick little pH calculation, and then I'll finish the rest of the notes. But if you got to go, or if you're kind of done with your brain's a little done, then you maybe you can leave if you want to. I'm just going to finish the notes because we're almost done. We're just doing a little bit more log math.
You think you can go up to the slide with the acidity, basicity real quick? Yes, that, oh, right below.
Yep.
Yeah. Thank you.
Yeah. Thank you, Jeremiah.
Got it. Thank you so much.
So when we're doing this math, you're literally just going to plug it in. Do not let it become something that makes you confused. So for part A, pH is equal to the negative log of the hydronium, which I'm giving you. Make sure that you know the pH is the negative log of hydronium, not hydroxide, because you will see problems like that. You have to do a little bit more math. So in my iPhone calculator, I have to type in the number first, 1.8 times 10 to the negative 4. I got to type that in first, then I press the log button. Okay, then I make it positive. Okay, or take the negative of it. Now, hopefully you're getting this number. I'm going to explain the sig figs in just a second. I think I have a slide for sig figs. Do I? I don't. I don't, but I need one. So hopefully you got 3.74, and you can do the next one, and you should get, it depends on your calculator, of course, how you're going to plug this in. Some of you need to plug the number in first and then press log, and some of you need to press negative log of and then to put the number in parentheses and everything. So hopefully this is what you're getting. And notice that my pH is different, my sig figs are different. So I have 2 sig figs here, but I have 3 sig figs here. So log sig figs are different. So your last sig fig rule you'll ever need to know. Okay, the last one. The number of sig figs in the concentration Okay, that's going to be your hydronium 4 hydroxide. And this goes for all logarithmic equations, not just pH and POH, but we're going to use it just for that, is equal to the, and here's where it's beautiful because it connects all your sig fig rules, is equal to the digits after the decimal place. Full circle, y'all. Full circle. In your pH or POH, depending on what you're talking about. Isn't that beautiful? So check it out. I got 2 sig figs in my concentration. Therefore, I have 2 digits after the decimal place. Professor Wakawa calls these DADP, if you want to just do that for short. DADP. Yeah? And it's reversible. So if you're going sig fig to concentration to pH, or you're going pH to concentration, the number of digits after the decimal in the pH is always equal to the number of sig figs in the concentration, no matter which way you go. It's your last sig fig rule. Shed a little tear. There's no more sig fig rules to learn. Clap. Are you excited that you don't have any more sig fig rules? That's it. That's your last sig fig rule. Okay. So again, if you're kind of dunsies with it today, that's fine. If you want to leave, I'm just going to keep going with the recording so you have a complete set of notes here. What if I give you the pH, but I want to know the concentration? So to get out of a log, okay, logs are base 10. You have to raise everything to the 10 to get rid of a log. And then we're just going to bring this little negative over here. There's more math to it. So my math folks, like, I'm not doing it exactly correctly, but I'm not teaching math right now, and we're not trying to teach the math. I just want you to know where it comes from, and then you can use it. Take this little negative. We're going to move it right here. I'm trying to draw something that looks decent. Okay. So I'm going to get, when I move this around, 10 to the negative pH is equal to my hydronium. That's how we get out of a log. You raise everything to base 10. Okay, and then we have to deal with that little negative sign. But guess what? I give this to you on the back of the periodic table. You don't have to memorize it. I give it to you. But I don't give you the OH one, but it's the same. Just take out your H and put your OH. Oh, also, you're given this one. This is going to be given on your periodic table. This is given. But you don't get the POH one. Just replace the H with the H and the OH. Okay, so in red are the ones you don't get. Need to know. And this is what you get on the periodic table. But they're exactly the same if you know how to just manipulate the OH to the H. So let's plug it in. Hydronium equals 10 to the negative pH. So that's 10 to the negative 4.80. Plug it in exactly like that. Like, I'm going to put, my iPhone has to be 4.8 to the negative, and make it negative. And then I have a 10 to the X button that I press and then does it. But your calculator, you might have to put in 10 raised to the, put in negative 4.8 and press enter. You should get 1.585 times 10 to the 1, 2, 3, 4, 5, negative 5. Give me sig figs. Use your new sig fig rule. I just put in my calculator. So by using my iPhone, I did 4.8, made it negative, and then pressed the 10 to the X button. If you're using a real calculator, you would need to probably put in 10 raised to the negative 4.8. So like 10 raised to the negative 4.8. Or maybe you got to put the whole thing in parentheses. It depends on your calculator. Don't use E. This is not something times 10 to the. Literally, this is the time when you get to do what you want, which is write 10 to the. So D, it's not going to be 1.59. What's my safe big rule? How many digits after the decimal place? 2 digits after the decimal place equals 2 sig figs. 1.6 times 10 to the negative 5. Boom. So, those of you that are math people, my physics folks, this is just a bunch of equations. You got to figure out which equation to use. So you really have to read the question, because if it's asking you for hydronium concentration and they give you pH, you can do this. What if I give you POH? You got to do some other stuff. I'm also going to give you another special situation. Because of this OH H3O plus connection to that KW we talked about a couple slides ago, if you're still with me, if you take the negative log of all those, what you get is 14 equals pH plus POH, and this will save you. You do not have this in the periodic table, though. This is special. Need to know. Now, you can do all this math without that, but it is a shortcut, and it will definitely save you some time. So if you want to go through the slides and make a list of the equations, I will box all your equations with this blue here. I don't have time to let you kind of write everything down right now, but if you want to go back into the notes and kind of look for these blue boxes, these are all your equations that you're going to be kind of using for this chapter, okay? And the ones that are highlighted are the ones you're given on your periodic table, and if it's not highlighted, then you kind of have to get it on your own. I'm going to let you do this. I will come back and do this one for the recording. And last topic is called a buffer. A buffer contains a weak acid and its conjugate base, meaning the conjugate base that goes with that buffer. Or with that weak acid, okay? And they resist change in pH. So what they do, your blood is a buffer, for example, and so your blood won't become too acidic or too basic. It will just stay the same pH no matter what you do to it, because it is a buffer. And we'll talk a little bit more about buffers after we talk about chapter 15, but just for right now, the definition, weak acid and its conjugate base. So an example of a weak acid, what is the conjugate base for HF? What is the conjugate base for hydrofluoric acid? F what? Not just F. You got to get rid of an H and you got to get rid of a plus, so F minus. Now, can I go to the lab, the stockroom, and just get some fluoride, some F minus? Nope. Any ideas on what I can ask the stockroom for that might have fluoride in it? So any soluble ionic compound with F minus in it works. So it could be, you could take hydrofluoric acid does not have a lot of F minus in it. Think about it. Hydrofluoric acid, it has like 1% F minus and 99% hydrofluoric acid. So it's not a really good source of F minus. Any ionic compound though is, if I take sodium fluoride, it only goes one way, right? 100% of it is fluoride because it's soluble in water. It dissolves in water. So you could have sodium fluoride. That's acceptable. That counts as a buffer. You could have magnesium fluoride. That counts as a buffer. Okay, anything with fluoride in it would still count as a buffer. Okay. So it has to be weak, not strong, and it has to be the conjugate base that goes with that acid. It has to be the pair. Notice they're both gonna have F in them. Okay. And this kind of just shows, we're gonna go through this a little bit more in chapter 10, so I'll kind of leave this for chapter 10. Or sorry, not 10. Whew, where am I? 15. So we're gonna kind of go over this a little bit more in chapter 15. I'll go over how it works, but you can read about it here if you want to, but I'll go over how it works. Okay, so I'm gonna go back and do some of this math and then post the recording. So we're technically done with class, so I'm gonna go through and do some math. So I would hope that you would do this math before, or should do this before you kind of look at these answers, but I'm gonna I'm not gonna record going through the math. I'm just gonna show you the work, because y'all can do this. Okay. All right. We will see y'all later. Goodbye. Text me with questions.